I want to start lecture 2 by talking about what the goal of this set of lecture videos is. And in this lecture and in some of the lectures coming up the beginning of next week, our goal is to talk about subgroups of a group. So today we're going to focus in on some special kinds of subgroups. We'll first talk about cyclic subgroups. Then we'll talk about subgroups generated by a subset. And then we'll define the lattice of subgroups of a group. So I want to start by giving you a definition from very early in Dummett and Foote. This is on page 20. Let's say G is a group and X is an element of G. The order of X is the smallest positive integer n such that X times X times X n times X to the n is the identity element of G. So a piece of notation that you should know, we write absolute value of X for the order of X. Okay, first, if there is no positive integer n such that X to the n is the identity, then we say X has infinite order. But that doesn't happen when G is a finite group. And why not? So if G is finite, the order of G is n, the size of the set G is, say, n, then let's take the first n plus 1 powers of x, x times x, x times x times x. Well, this is n plus 1 elements in G, which only has size n. So by the pigeonhole principle, 2 of these have to be the same. So the pigeonhole principle is this combinatorial thing. If you have n plus 1 pigeons, and only n pigeonholes, at least 2 pigeons need to go into the same hole. Whatever. Okay, so what does that mean? So there exist distinct I and j between 1 and n plus 1, where x to the I equals x to the j. So now if you just take these 2 equal group elements and multiply by x to the negative j, x inverse to the jth power, on the right, on both sides, you get x to the I minus j equals e. So just by switching the order here, we might as well suppose that I is bigger than j. If j was bigger than I, then we could multiply by x to the negative I. And this gives us some positive integer where x to that power is e, which means I don't know that that's the order of x, but the order of x is at most I minus j. So in particular, what does this say? The order of x is at most n, which is the largest this difference could be. Okay, I want to give one more key definition right now. A group is called cyclic if it can be generated by a single element. That is, if there's a special element, x, in your group such that G is equal to the set of all things that can be written as x to the n. So you let n vary over all integers. So that includes x to the minus 1 is x inverse. You have all the powers of x, all the powers of x inverse. So if there exists an x so that G can be written in this way, then G is called cyclic. We say that x is a generator for G, and we write that G is equal to angle brackets x. This notation is going to be really important. So what I'm going to do for the rest of this video is I'll pause and erase, and then we'll talk about some important properties of cyclic groups, which are the subject of section 2.3 of the textbook. Let's talk about some basic properties of cyclic groups. So cyclic groups are the subject of section 2.3 of the textbook, but I also really like a handout of Keith Conrad on cyclic groups that I'll post to the course website. So a first example, Z under addition is cyclic. It is generated by 1. Every element of Z can be written as 1 plus 1 plus 1 plus 1 plus 1 some number of times, where remember 1 to the minus 1 is the integer negative 1. So like 1 to the negative 10 is just minus 1 plus minus 1 plus minus 1. So Z is generated by 1 and is also generated by minus 1. And it's straightforward to see that those are the only 2 generators for the cyclic group Z. Okay, so why did I start this video with a discussion of the order of an element? Well, that comes from this proposition. Let's say G is a group and X is an element of G. Then this angle brackets X This is the set of all things. It can be written as x to the n where n is in Z. This is a subgroup of G. This is called the cyclic subgroup generated by X. So what's the point of this lecture? One thing that we're building towards is where do subgroups come from? Like, how do we take a group and understand the set of all of its subgroups? Well, one special kind of subgroup is you take any element X and you take the cyclic subgroup generated by X. Well, what is the size of that cyclic subgroup? That is the order of X. So the order of X, the smallest positive integer n, so that x to the n is the identity, is the cardinality of the cyclic subgroup generated by X. So how do you prove these things? Well, let me say something first about the proof of 1. I'm going to run out of space, so I'll pause and erase before I say anything about 2. The idea is to use this subgroup criterion from last time. So we know that H is a subgroup if and only if for all x, y in H, that implies x, y inverse is in H. So what does that mean in this case? Well, for any, I don't want to use x because I'm already using this for something else here. So let me say for any AB in the cyclic subgroup generated by X in this set here, we want to show that A times B inverse is also in this set. So we want AB inverse is in this set. And what do we know about these elements A and B? Well, like almost nothing, but we do know that they're in this set generated by X, so they can be written as x to some power. So we have we have let me do it this way, A equals x to the I, and B equals x to the j for some I and j. Right? A and B might be the same, so I and j might be the same. We don't know. But what does this mean? Well, then what is B inverse? B inverse now is just equal to x to the minus j. So A times B inverse is x to the I times x to the minus j, which is x to the I minus j, which is in this cyclic subgroup. So this is an example of how applying the subgroup criterion can be a pretty straightforward way to tell that something is a subgroup. Okay, so for the proof of 2, we have to do a little bit more. And what I'm going to do is pause and erase and take you through the highlights without doing all of the details. So let's prove the second statement, that the order of X is the cardinality of the cyclic subgroup generated by X. And we'll do this by splitting this statement into 2 cases. First, if the order of X is infinite, and then if the order of X is some finite positive integer n. This is really common with arguments about cyclic groups. When cyclic groups are infinite, you do one thing. When they're finite, you do another. So if the order of X is infinite, then x, x squared, x cubed, x to the 4th, those are all distinct. So that's not obvious. The reason for that is the argument that we just did before. If 2 of them were the same, if xi equals xj, then x to the I minus j would be equal to the identity. And in fact, the order wouldn't have been infinite at all. So that implies that all these elements are distinct, which means that the cardinality of the cyclic subgroup generated by X is infinite. So that's it. So the more interesting case is if the order of X is n, then x squared up to x to the n minus 1, by definition, are not equal to the identity. But x to the n equals the identity. So now we have these n elements. X to the 0, which is the same as the identity. X squared, x cubed, up to x to the n minus 1. And you want to show that these are all distinct. That these are n distinct elements of the cyclic subgroup generated by X. How do you do that? Well, if they were not distinct, you would have x to the I and x to the j that were equal to each other. So x to the I minus j would be equal to E. and I minus j would be less than n, which would contradict the assumption that the order of x was equal to n. So what does that give us? N distinct elements in this cyclic subgroup. So the order of the cyclic subgroup is at least n. Okay, so to conclude the proof, how do you show the size of a set is equal to n? You show that the size is at least n, and then you show that the size is at most n. So that's what we're going to do. And we're going to do that by taking x to the m for an arbitrary integer m, and we're going to show that it's equal to one of these n things. So that's going to tell us that there are at most n different elements of the cyclic subgroup generated by x. And in fact, then it'll say that the cyclic subgroup has size exactly n. And the key input here is the division algorithm. We're just going to let m be any integer. And we know that there's a unique r between 0 and n minus 1 and some integer q, so that you can write m equals q times n plus r. We're just writing m as something times n plus a remainder, right? That's why you pick r for this. Okay, so then x to the m is x to the q times n plus r, and that's the same as x to the n to the q times x to the r. To really justify this, I mean, we're just using the associative law in the group a bunch of times. X to the n is the identity. So that's the identity of the q times x to the r, which is just x to the r. So what have we seen? Any x to the m is equal to one of these n elements. And that's it. So now we've shown that the order of the element is the same thing as the cardinality of the cyclic subgroup that it generates. So I'm going to pause and erase and talk a little bit more about properties of cyclic groups. I want to talk about two important properties of cyclic groups. First, cyclic groups are abelian. How do you show that? Well, what does an element in a cyclic group generated by x look like? It's x to some power. So if you have x to one power times x to another power, it's the same as if you switch the order. So what do you actually have to do this really rigorously? Show that x to the a times x to the b equals x to the b times x to the a. So how do you really do this? Is it's associativity plus induction. So what do I mean? Just as an example, x squared times x, if you unwind what that means in the notation, that's x times x dot x. And that's the same by associativity as x times x dot x. So that's the same as x times x squared. So if you want to go from a equals 1 and b equals, a equals 2 and b equals 1 to arbitrary a and b, it's the same idea. You can do it by induction. Okay, so a more interesting property is that subgroups of cyclic groups are cyclic. So what we're going to do is let G be a cyclic group. So we can choose the generator, say it's generated by X, and let's say that H is a subgroup of G. If H is just the identity, I mean, that is always a subgroup. That's called the trivial subgroup. But that is the cyclic subgroup generated by the identity. So there's nothing to check there. Okay, so let's suppose that H is not equal to the identity. So there's one big idea here, which is we know H has some element in it that's not the identity. So it's x to some power. Maybe that power is negative. But then, because H is a subgroup, it's closed under inverses. So if you have x to a negative number, its inverse is x to a positive number. So that means H has some element that is x to a positive power. So what we can do is let D be the minimum positive integer such that x to the D is in H. This is the one key idea here. And what we're going to do is we're going to show that H is equal to the cyclic subgroup generated by x to the D. Well, okay, since x to the D is in H, it's clear that the cyclic subgroup generated by x to the D is contained in H, right? Because if you have x to the D, then you have x to the D times x to the D because H is a subgroup, it's closed under the operation and also closed under inverses. So you get the whole cyclic subgroup generated by this element. So the name of the game is we just have to show containment the other way. That everything in H is contained in the cyclic subgroup generated by D. Sorry, by x to the D. So let's just put this in one more step. Show that if you have an element y in H, that implies y is in the cyclic subgroup generated by x to the D. So y is in H, so it's in this subgroup generated by this group generated by x. So we know that y equals x to the m for some m. So we're going to use the same division algorithm that we just used before. That means that we can write m is equal to q times d plus r, where r is between 0 and d minus 1. Okay, so the last part of the proof is you want to show that m is a multiple of d, because that shows that y is in the cyclic subgroup generated by x to the d. So the things in here are exactly the x to something times d. So the question is, what happens if r is not equal to 0? So that's like the key thing in this argument. And we're going to get a contradiction, and the contradiction is that d is supposed to be the minimum positive integer such that x to the d is in H. If r is not 0, then you can take x to the m, multiply by x to the minus qd, which is in this subgroup generated by x to the d, and we would get that x to the r is in H, and r would be less than d. So that's the contradiction. So I said what the argument is out loud, but I didn't write down every detail. Hopefully, you can write down like a full proof for yourself at this point. So I'll pause and erase, and then we'll talk a little more about properties of cyclic groups. I want to state a few more important facts about cyclic groups. First, let's let G be an element of infinite order in a group G, big G, so little g and big G. When are two powers of this element of infinite order equal to each other? Well, they're equal to each other if and only if those powers are equal. And this idea now is one we've already seen a couple of times. If there were k and l that were not equal to each other, but g to the k equals g to the l, then we would have that g to the k minus l was the identity. So what's the corresponding fact for an element of order n? Well, if g is an element of order n, that means g to the n is the identity. So g to the k equals g to the l if and only if k is congruent to l mod n. What else does that mean? That means k minus l is divisible by n. So that means that g to the k minus l is g to the something times n, which is the identity raised to some power, which is the identity. So hopefully you can write down a full proof of this. So now I want to talk about subgroups inside cyclic groups. Every non-trivial subgroup of an infinite cyclic group has two generators, and those generators are inverses of each other. So how do you see this? Well, using this fact, you can see when the subgroup generated by g to the k is contained in the subgroup generated by g to the l, and in particular, that will tell you this fact. For finite groups, so let's say that G is a cyclic subgroup of order n generated by some element little g. If you take the subgroup generated by g to the k, that's the same thing as the subgroup generated by g to the greatest common divisor of k and n. Okay, how do you prove this one? This is a little more interesting. Let's show inclusion each way. Let's show that this first subgroup is contained in the second, and the second subgroup is contained in the first. The GCD of k and n divides k. So what does that mean? There's some power that you raise g to the GCD kn to get g to the k. So certainly the subgroup generated by g to the k is contained in this subgroup generated by g to the GCD, right? Because g to the k is in here clearly, which means the whole subgroup generated by g to the k is in this one. So the interesting direction is the inclusion the other way, that this one's contained in this one. And the idea now is the Euclidean algorithm tells us something about how you can write the GCD of two numbers. It says there exist integers a and b such that the GCD of k and n is some integer times k plus some integer times n, that it's a linear combination with integer coefficients. So now let's just replace this GCD kn with ak plus bn. G to the bn is the identity. So now you get this is g to the ak, and now inclusion this way is clear. So when is the subgroup generated by g to the r equal to the whole group? Well, the subgroup generated by g to the r is the same as the subgroup generated by g to the GCD of r and n. Well, if that GCD is 1, then the subgroup generated by g to the r is the same as the subgroup generated by g to the 1, which is the whole group. And the other direction also holds. If the GCD is bigger than 1, then you get a subgroup that's strictly smaller. If you have a number that divides n, then you're getting a smaller subgroup than the whole group. So what does this tell you? It tells you the number of generators of a cyclic group of size n is the number of numbers between 1 and n that have GCD 1 with n. And there's a name for this. This is the Euler Totient function, which is usually written with this phi of n notation. So I just want to give one more consequence of this proposition before moving on to something a little bit different. So I'll pause and erase and then talk about one last thing. The last thing I want to say now about cyclic groups is this classification of subgroups of a finite cyclic group of order n. And what this says is there's a bijection between subgroups of a cyclic group of order n and divisors of n. So the key thing is this proposition that tells you any cyclic subgroup of this cyclic group of order n, you might as well take a generator to be g to some number that divides n. Right? So we know that every subgroup of this group has to be cyclic, and every cyclic subgroup is generated by g to some divisor of n. So that means that there's at most one subgroup of order d for each divisor of n. And then how do you know that those subgroups are all different? Well, for one thing, they all have different size. So if d divides n, then the subgroup generated by x to the d has size n divided by d. Just as a little check, put in d equals 1, and you get n. So everything is good. So this is a little bit quick, but I hope that you can write down a full proof of this. It'll be good practice for the types of arguments that we've talked about so far in this first video.